Hey everyone, in this video, we're going to look at the second part of section 5.5, where we use integral tables to compute integrals. Now, as I outlined in our overview for section 5.5, using integral tables is kind of starting to become irrelevant as we rely on other technologies like internet, the computer. But it's still important to use these tables to be familiar with the types of integrals that we might frequently come across. So the table of integrals that I have provided for you comes from a textbook by James Stewart. I just find it the most comprehensive collection of integral formulas. It's about 4 pages, so pretty long. And the more problems that we do in this section, the more familiar you'll start to be with the types of integrals that you see here. So you do not need to memorize these integrals, but it is good the more problems and practices we do to become familiar, again, with those types of integrals that come up frequently. And the reason why we have these integral tables is that because mathematicians, scientists, engineers have come across integrals multiple times and have recognized that going through the process of partial fraction decomposition or U sub or integration by parts can be kind of cumbersome and clunky. So they've just recorded those solutions of some common integrals. Okay, so now back to our workbook. So let's start by looking at example 4. So in example 4, because we're in this integration using tables section, we know that we're going to use our integral table. But first, we're asked to complete the square. So what we're given here is an integral, a rational function. So completing the square in this case means completing the square for that denominator function. So let's take a moment to describe how we would do that. So we are given x squared plus 6x plus 13. Now, if it's been a while for you seeing work on completing the square, or maybe you haven't come across this algebraic topic in a while, I have linked for you a pretty interesting Wikipedia page that describes some reasoning and visuals for what completing the square is and why we might want to do it. But I'll say a few words here too. So the goal of completing a square or completing the square is to rewrite a quadratic expression like this, so a polynomial of degree 2, such that the first 2 terms involving x becomes x plus some a squared. Now, what happens when we do that is that we introduce some extra junk here in the a squared when we FOIL out this x plus a. So what ends up happening is that we have to compensate by subtracting that out in the end. Okay, so let's go through this and I'll say a little bit more as we do so. Okay, so I'm going to rewrite this a little differently. So x squared plus 6x plus 13. So that's our expression that we have. And I want to rewrite this part as x plus some b squared. So how might I do that? So if we have x squared plus 6x, I want that to equal x plus b squared. So what does x plus b squared look like? Well, we have to FOIL it out. When we do that, we get an x squared term followed by a 2bx term, that's taking the outsides insides, followed by a plus b squared. So if we want these two things to be equal, then just as we saw with finding the numerators in a partial fraction decomposition, we need each of the like terms to be the same. Okay, we have an x squared on both sides, so check, that just works out. But now our x term, on the right-hand side, we have 2b. On the left-hand side, we have 6. So that means 6 has to equal 2b, which would then mean 3 is equal to b. So we could write a 3 here. But that would mean this right-hand side has an extra plus 3 squared or plus 9. So to compensate for that, we need to subtract a 9 in the original expression. So let me write that out so we see it together. So if I'm going to substitute my first part here, that, again, when I FOIL it out, we'll have almost all of the right parts that we need. but then it will also have a plus 9. So typically what is done then is that we subtract the 9 in order for our original expression to stay balanced. So then what that would look like, this first part here becomes that lovely x plus 3 squared. And then we combine our numbers here. So -9 plus 13 would become plus 4. So that means that our original denominator of x squared plus 6x plus 13 is equal to x squared plus 6x plus 9 minus 9 plus 13, which then simplifies to just x squared plus 3, x plus 3 squared plus 4. Okay, that green highlighter and green pen is just lovely, isn't it? So let's just rewrite what we have here. So this means the integral that we have, let's write integral, is also equal to the integral of 1 over x plus 3 squared plus 4. All right, so pause the video right now, make sure we're all cut up, and I'll erase this initial work so that we have more room for the second part. All right, so now we're told, after completing the square, to substitute to evaluate this integral. So we can recognize that the substitution we'd want to use is u is equal to x plus 3. And that's because we can see that x plus 3 expression is kind of the most inside function, and that's typically the function or expression that we want to use for our u sub. So I'm going to let u equal x plus 3. So my du becomes dx. So then my integral, when I translate it into u, becomes 1 over u squared plus 4 du. And I should have put a dx here. Nice job if you caught that. All right, so because we're using our integral table in this section, let's take a look at our integral table and see if we can find any integrals that have a similar form of the one that we just found. All right, so we have a u squared plus a 4 in the denominator. And one little thing we can recognize here too is that 4 is also 2 squared. So if we need 2 squares in the denominator, we can also look for a function or integral of that form. All right, so we see that we do have a very similar integral here. Formula 17 becomes used quite often. We think we've already seen it in an example in our class. So this looks very similar to what we have. We have a du, we have a u squared in the denominator, and then we also have a 4 in the denominator. So if we let 4 equal a squared, that would mean a is equal to 2. So our problem, our integral, looks very similar to 17 with a equal 2. So that means the solution of our integral looks like this. So I'll go ahead and copy that over for us on the other page, where every time I see an a, I'm going to put in a 2. So that looks like the following. And whenever we use the integral table, I always want to cite it. So I'm going to say using integral number 17. That way, if somebody else is looking at your work or if you're explaining it to a team member, you can remember where that integral came from. So that becomes 1/2. Again, I'm always going to use 2 for a, arctan of u over 2 plus c. So now we're almost finished, and let's just double check that I had that right. Awesome. I like to use arctan instead of tan to the -1, just because sometimes the power of -1 can be ambiguous, whether or not that -1 means the inverse or whether it means 1 over that function. So we're just being really clear here. Okay, so we're looking pretty good there, but what's the final thing that we need to do before we're completely finished with this problem? We need to translate back into x's. So we need to substitute in u equals x plus 3. So what does that look like for us? Then our integral becomes 1/2 arctan of x plus 3 over 2 plus c. So that means our final answer is given here.